In this video, we'll see how a capacitor and a spring are analogous to each other, since both of them can store energy, hence their energies are equivalent. Here, charge Q stored in the capacitor is equivalent to extension x of the spring. Also, capacitance C is equivalent to the reciprocal of K, and obviously the current is equivalent to the velocity. So connecting just the capacitor with the battery is like applying a force on the free end of the massless spring. In both cases, the capacitor will be fully charged and spring will be fully extended almost instantly, where the charge over capacitor is CE and extension in the spring is X. Also, work done by battery is CV square, but only half of it gets stored in capacitor, so the other half is dissipated as heat. Similarly, work done by force is Fx, that is F squared by K, but half of it is dissipated as heat. Let's connect the capacitor with an inductor in series, which is same as connecting a spring with a mass. Note that there are two cases, one when the capacitor is initially charged and the other when it is not. The first case is the same as having a maximum extension in the spring. Since the spring will now come to its mean position and advance towards its left extremer, hence the displacement of the block will be given by x equals to a cos omega t, and we can get the velocity by differentiating the displacement function. Similarly, for the given circuit, we can write the similar functions for charge and current, and so their graph would be similar to its mechanical counterpart. Let's verify the same using SymPhy, where an initial charge is given to the capacitor and its voltage and current graph is as shown. Note, charge and voltage graphs are similar, and the only difference between the two is of the amplitude, as Q equals to CV. Hence, the time period and omega for both the scenarios are same, and so is the energy equation. For the second case, where the capacitor is uncharged, is the same as no initial extension in the spring, and so the spring will expand to its mean position and travel further to its right extremer. Hence, the amplitude is equal to F by K, and the maximum extension is equal to twice of the amplitude. Similarly, the charge at the capacitor at equilibrium, that is when the current is max, is CE, and its function with time is CE minus CE cos omega t. Differentiating it, we can arrive the current function as CE omega sin omega t. Both scenarios will have the same graph, where you can note the spring never has a compression in it. Similarly, the polarity of the capacitor never changes. In the next video, we'll see another interesting similarity. Don't forget to like and subscribe the channel.